The next type of aromatic reaction that we're going to work with is called the nucleophilic aromatic substitution. And pay special attention to the name. Nucleophilic, as opposed to electrophilic, involves a nucleophilic reagent reacting with the ring instead of an electrophile. Now, just a couple of things when dealing with this type of reaction. First is that it's only possible with aryl halides that contain other electron withdrawing substituents on the ring. Also, you're going to need a good nucleophile like hydroxide, alkoxide, or an amide. So let's take a look at an example. Here we have an aryl chloride, and I'm going to put 3 nitro groups on the ring at the ortho and para positions. If we react this with hydroxide, the hydroxide will replace the chlorine. Now we get the hydroxide that replaced the chlorine, and since the hydroxide is a nucleophile, it's nucleophilic aromatic substitution. Now this particular example was chosen carefully because the nitro groups were ortho and para to the chlorine. And it is an important feature to realize that you need these electron withdrawing substituents at the ortho and or para positions. You don't need multiple nitro groups, just one will suffice. But we do need them to be orthopara. So just to compare a couple of examples. Here we have a para-nitro versus a meta-nitro. Now if we use, let's say we use sodium methoxide as our nucleophile. Okay, if you see this where we have a metal bonded to a non-metal, just think about Na plus, OCH3 minus. This is in fact a nucleophile. Now, in the case of having the nitro group para to the chlorine, the reaction does work. And we end up with the methoxy group substituting the chlorine. In the case of the meta-nitro group, the reaction does not occur. And this has to do with stabilization of the intermediate. So the best way to look at this is by going through the mechanism. So we can see exactly what's happening. If we have the nitro group at the para position, let's react it with our nucleophile. The nucleophile attacks the carbon containing the halogen. We call this addition. And we're going to send, since we can't have 4 bonds on this carbon, let's put a negative charge on the ring. chlorine, our OCH3, and when we pushed these pi electrons over onto this carbon, that's how we get the negative charge. Now, through resonance, we can move this negative charge around the ring, and we'll just show one resonance structure here. That puts the negative charge on the carbon containing the nitro group. This really helps to stabilize the negative charge. So it's really this particular resonance structure that lowers the energy of the mechanism enough to for this reaction to occur. Now, from this particular intermediate, what we can do is show this lone pair from the negative charge going back down to reform aromaticity in the ring along with loss of the chloride. And this step of the mechanism is called elimination. So overall, we call this an addition elimination mechanism. When the nitro is at the meta position, if we try to do addition, we can add there. We can put the negative charge on this carbon like we did before. But then, if you move this negative charge around the ring through resonance, you're only going to be able to get it at a few different positions. So we can get it here, we can move it to here, and we can move it to here. We're never able to get the negative charge on the carbon next to the nitro group, so we don't get that extra stabilization of the withdrawing group stabilizing the negative charge. So that's why when you have the nitro meta to the chlorine, this reaction does not occur. You don't get that extra stabilization. The next type of nucleophilic addition reaction of aromatic rings we're going to look at is often considered a benzine type reaction, and we'll see why it gets this name once we get into it. But just consider the following two examples that I have shown here. In both cases we have an aryl halide. There's no extra electron withdrawing groups attached. But if I take this aryl chloride and react that with sodium hydroxide and water with very high temperatures, about 350 degrees, I can replace the chlorine with an OH group. And that would be the OH group from NaOH. Similarly, if I take this aryl bromide or another aryl halide, it doesn't necessarily have to be the bromide, and react that with potassium amide and ammonia, then I can replace the bromine with the NH2 group. And this particular reaction is pretty important because it provides us an alternative to get to aniline and aniline derivatives, as opposed to nitration followed by reduction. So what this is basically a substitution of halobenzenes with strong nucleophiles that are also bases. Now let's consider an experiment that was performed. Bromobenzene was taken, and the position where the bromine is attached was isotopically labeled as carbon-13 to identify it from the other 5 carbons in the ring. This substrate was then reacted with KNH2 and ammonia. When you see this KNH2, just think of it as a nucleophile, K plus, NH2 minus, so that is, of course, a nucleophilic species. And the products of the reaction, first observed, was as expected, the NH2 group attached to the labeled carbon, replacing the bromine. But somewhat unexpected was a second product where the NH2 group ended up on the carbon adjacent to the isotopically labeled carbon. So this particular result prompted an investigation into the mechanism, and the mechanism that was proposed is known as the Benzine Mechanism. And basically, what is thought is going on here, you start with your aryl halide, and I'm going to draw in one of the hydrogen. First, this reacts with the amide, which is a strong base, and rather than adding into the ring, we can do an elimination, eliminating HBr from the molecule. What we do now is add a second pi bond across this portion of the ring. We have a triple bond in the ring, and this is a very unstable intermediate known as benzine. The benzine is very reactive, so from here another molecule of amide, NH2- can act as a nucleophile, and let's go ahead and keep this carbon labeled as carbon-13. This NH2- could add to either side of this triple bond. Okay, for this purpose, let's just add it on the carbon adjacent to the labeled carbon. We've added it here. We push these 2 pi electrons over onto this labeled carbon, giving us a negative charge there. Remember, we start here with a triple bond. We push 2 electrons over, so now we have a double bond with a negative charge. Now, this takes a proton from ammonia. So the negative will come down and grab the proton. Giving us our final product with the NH2 group adjacent to the labeled carbon. Okay, now it's also possible, and equally likely, that instead of attacking the carbon adjacent to the isotopically labeled carbon, it could attack the labeled carbon. In that case, we get the NH2 group on the labeled carbon, and then after this picks up a proton, we get the other product. So this shows exactly how through the mechanism the NH2 group is added to the ring. Let's take a look at an example using benzene as an intermediate. And we're going to work with a bromobenzene that is tri-substituted. And we'll react this. We'll use sodium amide instead of potassium amide this time. And ammonia. So the best thing to do is first draw your benzene intermediate. Well, you need to lose HBr from the molecule. Well, the only place we can do that from is right here. Because this particular carbon has a methyl group, there's not a hydrogen you can lose. So let's start by drawing our benzene intermediate. Then from here, once this reacts with NH2- as a nucleophile, it can add to either of these triple bond carbons. So draw products for both. If it adds to the top carbon, we get this product. If it adds to the bottom carbon, we get this other isomer.